In the previous video, we talked about, uh, I think it was about vectors. Yeah, we definitely talked about vectors. So in the previous video, we talked about vectors, and I was wrong in that video when I said that I was talking about matrices. Before that, I actually talked about uh, metric, the metric before that. Yeah, metric over spaces, metrizable spaces and stuff like that. But metrizable space and the like belong in topology, and that's not really what I'm going to be discussing. I think I'm going to be applying some topology. A majority of topics from topology have already been integrated into my theory, or the theory that I'm currently working on, which is person theory. I think I'm going to link the paper down below. It's of course still a work in progress, as is most theories nowadays. Um, and it's a solid theory, and it's a great way for me to codify and abstract things that we human do, or what things that we human are composed of, like identities and stuff like that. The thoughts that we have in our mind, literally our brain, or the interactions we have with other people. The idea is it's immense, and I'm just getting started with the paper. If you think that the 5 pages that the paper is right now is all it is, you're dead wrong. That is just the beginning. Oh boy, does it have a lot of applications or interconnections between various fields in pure mathematics. So the small plan is that, okay, this video I'm going to be talking about proofs, or making proofs, and then the next video I'm going to be discussing about imaginary numbers and the complex plane and maybe holomorphic functions, which are very interesting actually when we start thinking about differentiation and taking limits in the complex plane. It's not like the usual epsilon delta definition that you guys know, but it's something else. It's something more than that. It's something that includes or involves two spaces, or two product spaces, and mappings between those two spaces. And actually, this is a small thing that I did to demonstrate it to I was trying to teach someone in Discord the intuition behind taking limits in the complex plane, and that's sort of where I got the idea for the video. So yeah, that's the next one after this one, and after that is after the imaginary part video is where I'm gonna talk about structures, mathematical structures, not the structures that structural engineers build in real life. We're talking about sets that contain some rules. So structure, mathematical structure, means that a set or something or collection has rules. But today's video we're going to be talking about proofs. And proving things is a very important concept in mathematics itself. And it's used in almost every crevice of mathematics except elementary math. Of course, they don't force you to prove 1 plus 1 equals 2 via successors, right? No, they don't. But once you guys start getting to geometry, you guys remember that you guys are required to make proofs that two triangles are equivalent, or something like that, via some postulates or axioms. And in fact, when you guys start getting into set theory and logic and topology itself, proving things is going to be an important topic for you guys to learn. So I'm going to give you guys the overview of what proving is and the various proofs, or at least the proofs that I know, for you guys to get started on these things. So before I teach you guys some algebra, or some abstract algebra, I know I actually already did with groups and orbits, it's important for me to lay down one of the most important things that we pure mathematicians do, and that is prove things. So, as you guys may know, a proof is basically for a reinforcement of a statement. So if we have a statement, let's say, this is a pencil, well, right, to a blind person or to a person that's not seeing the pencil right now, you need to prove it to them that you're holding a pencil. And of course, that's holding it right in front of their face and saying that is. Or describing what you're holding. I'm holding a pencil, and they're like, oh, prove that. Well, a pencil, as you know, is yellow. And it's like, yes, but there are other things that are yellow. And so you say, well, it's cylindrical. It has 6 sides, like a hexagonic cylinder. The top part tapers into a tip, such that when you put the tip on a surface, it marks the surface, right? And they're like, yeah, go on, but that could be a marker or that could be a pen. And I'm saying, well, the definitive way to end this is to say that it is made of wood. And it's like, oh, I'm convinced you really are holding a pencil in your hand. So that's what we basically do in proofs. What we do in proofs is try to prove something true, to show that a certain something is what it is. And the most basic premise of how to do proofs is we break down the proofs. Or so we have a statement, and then we start with an assumption, a fundamental assumption, and use logic to build our way towards the result. So when you discover something or invent something or discover something from, say, logic and exploring with a bunch of axioms or predetermined statements that are true in and of themselves, when during the discovery process, if you've written that, there's a high likelihood that a majority of that exploration that you've written down is the proof, right? So you note down your logic and how you got that result and show why that logic is true. So there are actually 2 main ways that I know for you guys to prove something. So the first one is proof by direct proof. And direct proof is when you basically lay down all the logic in one go and directly say or directly prove that something is true or a certain statement is true, right? So let's say that given a simple equation, x squared minus 4 equals 0. So prove that x equals 2 is the solution. The simplest proof and most direct proof is simply plugging this inside. So x is equal to 2. And we're showing that if we put 2 into this equation, it would equal 0. So that's 2 squared minus 4 equals 0. That 2 squared becomes 4. 4 minus 4 equals 0. 0 equals 0. So it's true. That's our proof. End proof. There are many ways to end your proof. Majority of mathematicians write QED, which stands for quod erat demonstrandum. And quod erat demonstrandum basically means as was to be shown, or what we want to show, as is what we wanted to show, or as is demonstrated. Quod erat demonstrandum, or QED. Or they write this box here, which I like doing. I like writing a box and then shading it. You guys see it in my lectures. That's how I end proofs. And that's called a halmos. Alright, so this is a great way, this is a way that a majority of mathematicians prove their statements. This is the most common way people prove statements. And the second one is proof via contradiction. So what we're doing is that we're trying to invalidate other truths so that the truth that we want to be true is the only thing that can be true. So we have to force the reader to accept that no other thing is true except the thing that we want them to be true by showing that that certain thing that is not what we want does not hold, is not true. So this time, let's say, or prove this time that x equals 3 is not the solution to this equation. So prove that, okay, so what we're doing by contradiction is that we're going to prove that any other number that is not 2 is not the solution to this equation. So I'm not going to write here prove that, but this is the first proof. This is proof 1. We're proving that indeed this is the solution to that equation and it makes it true. And proof 2 basically tells us that the number 3 or any other number that isn't 2 is not a solution to this. So proof 2, let's assume that x is not equal to 2 and can never be 2. And let's also make another assumption. Assume x is equal to 3. So now this time, we're trying to prove that no other number or integer can solve this equation except 2 by showing that it does not equal 0 when we plug 3 in. So 3 squared minus 4 equals 0. That's 9 minus 4 equals 0. And that's 5 equals 0, which is not true. 5 is, of course, not equal to 0. And so that proves that no other number, or rather the number 3, cannot be a solution to 2. And there's another way to prove that no other number can be a solution to this equation except 2, but that will require a bunch of generalization and another kind of proving called induction. And induction is a way of proving certain statements such as formulae. When you want to prove a certain formula is true for any number that you can think of or any integer that's above 1, you basically start by proving that 1 does satisfy the equation and then saying that a certain number k when plugged, or k plus 1, when plugged into the equation just yields the formula that we were given with, right? So we're proving that for any number that's greater than 1, k plus 1, the formula holds, and that, or rather, it gives us the formula. So in general, when we write a proof, what we're given, or the first thing we write, is an assumption, a fundamental assumption. So given a bunch of postulates or axioms. Now postulates and axioms, or a given theorem that's already proven, are statements that we use or we base our logic off of. So without axioms or postulates, there cannot be proofs. No proofs would exist without any underlying assumptions. Because when we say that a statement is true without proof, that is an axiom. That is a postulate. So a statement is true in and of itself, or it is self-evident, that is an axiom or a postulate. And that is where we base all our logic from. So we begin with a fundamental assumption, and then we start saying let something, something, something. Especially when we use induction, we say let this thing be that thing, and then from there we build the logic. So the second step is use logic. And what we do is break down the logic into various parts and prove that those parts, via the fundamental assumptions, are true. And when we use the logic to prove that certain parts of the statement or certain parts of our derivation is true, that's when the whole becomes very solid and very undetestable. So when we use, break down the proof, break down the proof into mini proofs, and show that they are true under number 1. So this is why in your geometry classes they ask you to sort of prove that certain parts of a triangle are equivalent to the other triangle before saying the whole is equivalent. So it's a sort of way of saying, or what I did a while ago with the pencil, is we break it down into the components of what a pencil is fundamentally made of, and then show or say that we have those in our hands constructed together to give the person the proof that we are in fact holding a pencil. So we proved via describing the various parts of the pencil that we are holding a pencil in our hand to a person that's not or that cannot see us hold the pencil, right? So we break it down. That's the most important part of a proof. That is, we break down the proof into various parts which we show, or actually we break down the assumption or the statement we're trying to prove, right? We break it down into various parts which we show to be true according to some logic plus these fundamental assumptions that we had in the first place. And so after we've done the breaking down and then showing that all parts of our assumption are true, or all parts of the statement are true, we say QED, or the proof is done. So when we finish doing a proof, we write QED or draw the Halmos box, whatever you name it. So the two most prevalent, just to summarize things, the two most prevalent proofs in the mathematical literature is the proof or direct proof and the proof by contradiction. Direct proof is when we directly prove that a statement is true by breaking it down into its parts and showing those parts of the statement, or rather the derivation of those parts, are true according to some fundamental assumptions we have. And the second one, proof by contradiction, is that we are proving that no other statement is true in our case except the one that we want to be true by showing or by breaking down the components of those false truths and proving that they are indeed false and the thing that we want to be true is the only thing that is true. And so that is it for proofs. So again, next video is gonna be about imaginary numbers, and after that, after imaginary numbers, we're gonna jump on to start discussing about abstract structures or mathematical structures, which are sets that contain some additional rules and stuff like that. And these things are really the fundamentals of math. They're the building blocks on where the math that you guys know is built from, where the calculus that you're taught in AP is built from, where the addition and subtraction of numbers from your elementary school days come from. This is where these come from. So basically, the theory behind the theory of math. So the math behind math. This is really what I'm building towards. And this is what the foundations of math are. So that's pretty much it for this video, and see ya.